Yes,
I cannot do it without the host trust.
I did it. So, yeah. We are recording now.
Okay, hello everybody. Thank you for inviting me. So I will talk about these artificial neural networks over graded vector spaces. And the first thing is to give you some kind of motivation, at least from my point of view, how I got into this problem and what does that mean. So I'm by training an algebraic geometer, and I'm studying or at least have been trying to look at things like algebraic curves and that kind of stuff. And so the moduli space of algebraic curves, normally genus 2 curves, but it's something that I've been interested. And a few years ago, maybe about 3 years ago, we started this project of trying to study the moduli space of curves, maybe by using some AI or some kind of artificial intelligence. And so this is actually a paper that took a long time, but it's actually out this year. So in this Journal of Algebraic Combinatorics, you might want to look at it if you are interested in that kind of stuff. But so what's the idea? We want to create a database of genus 2 curves. And if you don't know what they are, don't worry about it. I mean, they are algebraic curves that look like this. So these A0 through A6 are coefficients. Normally we study them over the rational numbers, but you can study them over any field. And so and the discriminant of this thing on the right is not zero, okay? So equations like this. And one way to create a database, of course, is to just generate these tuples A0 through A6. So these 7 tuples. And we created a large database like that and try to do something with that. So some of the things we wanted to do is estimate or at least try to guess things like what is the automorphism group of these things, whether the Jacobian is split or not, and so on. By the way, so they are actually very, very important in things like cryptography, isogeny-based cryptography, which is post-quantum. And so there's a lot of interest to other people as well about these curves. From my point of view, I mean, this is kind of going back to my thesis 20 years ago. So anyway, so one fact from algebraic geometry is that 2 such curves are isomorphic if and only if they have this invariance of the curves. So you define this Igusa invariance. Now, I didn't type them here, I could have. They are polynomials. Each one of them is a polynomial of degree the subscript. So J2 is a polynomial of degree 2 in terms of the coefficients of the curve. So if I take these curves here, this curve as above, and the coefficients are parameters, J2 is a degree 2 polynomial in terms of A0 through A6, and J4 polynomial of degree 4, and so on. So these are called invariants, and the subscript 2 and 4 and so on is called the weight of that invariant or the grade of that invariant. Okay, so these are homogeneous polynomials. So I created the database with the coefficients, but also I created the database with the invariants. Now, the way that these two curves are isomorphic is not exactly the same invariance, but invariance up to some multiple. And that would be the whole point of our structure, basically. So if you take another curve isomorphic to this one, and you compute the invariance of that this invariance here and the invariance of the new curve will be connected. They will be multiplied by some constant, but that multiplication, that is not the scalar multiplication that we use in linear algebra, but is kind of a scaled one. So if that constant is some lambda, this will be lambda squared times J2, lambda to the 4th times J4, and so on. So technically, that means they are points in a weighted projective space. We say mathematically. Anyway, you could actually, scale them the right way, so find the so-called algebraic invariance or absolute invariance or affine invariance by dividing by one of these invariants. And J10 is the discriminant. I know that's never zero, so I'm dividing by J10. I mean, there is actually a typo in this. So this one here, notice the numerator here, 2 times 5 is 10 plus 10 is 20. So the denominator here should be J10 square. So these combined degrees of these combining with the weight should be the same for each one of them. So I missed all three of them. So this should be actually to the cube, and this should be to, what is that? 6 times 4 is 30 plus 30, so 6. So this should be to the 6. So I missed all three of them. Anyway, now this is important here. So two genus 2 curves are important are isomorphic if and only if they have the same triple of this invariance I1, I2, I3. So, being naive about this, I never done any machine learning kind of thing with these things. I created a database, created a dictionary in Python, and this triple of invariance is my key. So my database, which at the time was over 1 million curves or so, 1 million isomorphism classes of curves, so over 1 million entries of these triples like this. This was the key. That doesn't repeat, so I know I don't have repetition in my database at all. But of course, we did do it both sides. So I started with a database of the coefficients, and we try to figure out the automorphism group, and we try to figure out this splitting of the Jacobians and so on. But just to make sure, you know that I know how to do these things mathematically. I have algorithms for them. So my data did not have any errors, any noise or anything. Everything is actually generated algorithmically. So I'm not trying to do this to find new mathematics. I'm just trying to see if I can do this using machine learning. And so using the database of coefficients, the best we could do was about 60 or something percent. So this was the highest we can get, 67% accuracy in, for example, determining the automorphism groups or determining the splitting of 2 by 2 or 3 by 3 Jacobians. But when we actually say, yeah, forget about these coefficients, we just want to take the database of invariants. So the database of invariants was almost all the time perfect. So it got very high accuracy. And we still don't know at this point, like, why that is. And there are mathematical reasons why I thought that's the case. One thing is that, well, now data has no repetitions, no double classes, but when you have invariants, of course, you have many tuples of invariants. When you have coefficients, you have many tuples of coefficients corresponding to the same curve. And so, of course, that might have something to do with that. But there was a technical problem in this. If you actually run the data with these triples of invariance, this absolute invariance, what is happening is that you will take these J2, J4, and J10 and so on, which are very large numbers, and you have to increase them to even higher powers. Look at this, J6 to the 5th, J10, which is huge, to the cube. So that will be increased to very large numbers. So this I1, I2, I3, we are talking very quickly, you are going to 20, 30 digits. So very quickly, the computations kind of reach at the point that you cannot continue. And so the very natural thing is, well, I have this invariance here. I have this tuple of invariants. Somehow the information is encoded here. I'm not doing anything. I'm not gaining any new information by getting here other than raising them to some powers. So we should somehow be able to figure out things here. We should be able to do some machine learning or do some computation just with this invariance. And like I said, the trick here is that these are not tuples, these are not vectors, these are not tuples in a vector space because the scalar multiplication doesn't quite work here. The way we are used to is this scaled scalar multiplication. And well, I knew from other things in algebra that this is actually a graded ring, and a graded ring meaning that is a ring of polynomials where every polynomial is graded differently. So in this case, these grades were 2, 4, 6, and 10. And so this was where it started. And then the idea is, can we actually see if we can do this over some vector spaces with some grades? And that's how we got to these graded vector spaces. Now, graded vector spaces are something that not very popular, even though they've been studied for a long time. And I had to go back in the 60s from Bourbaki to find a nice chapter there in algebra book about this. And then I noticed that there are a few other things. And the main question, and that's kind of what it is for this talk, the main question is, can I actually construct and build a whole machinery of neural networks and transformers and LLMs and all that, but do this not over a vector space, but over a graded vector space? Now, before we get into the technicalities, because eventually this does get a little technical at some point, why would we want to do that? I mean, is there any reason from the machine learning point of view that we want to do that? First. And second, can it be done mathematically? And third, I mean, if it can be done, does it make sense? Is it efficient or not? I mean, so some of these things we will discuss today. But at least from a intuitive point of view, if you have a vector, you have the input features on a model, it's reasonable to expect that not all features are equally important. So having different weights for different coordinates of a vector might actually make a lot of sense, and at least in some applications. I give you like one simple thing. I mean, my brother is involved in this self-driving and automotive, self-driving and EVs and all that kind of stuff. And so sometimes talking to him about these things, I mean, he gave me right away one example. He said, look, let's say you are in self-driving, I mean, a car. I mean, don't run over, don't kill anybody. It should have more priority that maintain speed, maintain current speed, and things like that. And you can think of many applications and situations where these things hopefully would make more sense. At least in my case, in the case of moduli spaces, they definitely seem to fit right in perfectly in that situation. So let's just see if we can make this work and see how mathematically this could this could work out. So okay, we all kind of, I expect in this seminar, we all kind of know a little bit the general setup. So we have what? A neural network model, which is a map from K is a field here, okay? And just think of R, but in any case, characteristic 0, so I'm not going to mess with anything fancy here. So it's a map from Kn to Km, right? And the input vector or the vector in Kn, we call it the input features, and what gets out is the output features, yes? And we have neurons, which are basically, maps where you have G of, these are the weights. And again, these weights here are different from the weights that I will talk at some other points, the grades of this vector space. Yeah, so just to make sure we understand that. In a lot of mathematics, these graded vector spaces are called weighted spaces. And I made a point to stick with grades because I didn't want to have in the same kind of paper weights, meaning two different things. But you will see a lot of things in mathematics, they are called weighted spaces. Anyway, so these are the weights of the model of the network. And this is some kind of a bias vector that we call it. Okay, so this is a single neuron. We have the layers of the neuron where we actually perform this multiple times, depending of the kind of model you're building. So now this vector B here is, this bold B is a vector. Okay, and so a composition of this of these neurons, it's what we call a neural network. So something that looks like this. Okay, again, I'm not trying to get to the bottom of this now. I know you know this stuff, but it's kind of important because I will try to define this now for the graded vector spaces. Okay, so well, let's see. So for these neural networks, at least what made it kind of work, the whole thing click, was that there was this result of Cybenko, I believe I hope I have the right year here, 89, I believe, is that, well, any non-constant bounded monotone increasing function, then this can be actually approximated by these neural networks. Okay, so let me just state this the theorem the correct way. Okay, so the set of functions of this form, okay, when x is a vector in Rn and these are the parameters, is dense in the space of continuous functions on some compact set. Okay, so in other words, what that means is that we can, since it is dense, okay, so we can actually approximate using these activations any continuous function on compact sets. Okay, there was actually another result kind of at the same time, which said basically that if you have this again, K is a compact set of Rn, and M is a positive integer. So we have now this set of continuous non-decreasing functions such that the limit when x goes to infinity is 1, okay, and 0 when it goes to minus infinity, then the set of such functions can be also approximated, up to whatever accuracy that you want. So your f of x basically is the distance with this activation functions, right? It's arbitrary. They could be arbitrary close. That's kind of what makes it work. At least theoretically, we know that if I have a function through a model, I can always, eventually get approximated and get close to it. So that's what we will aim for. Okay, so let's just start small here. I want to define what is a graded vector space and over some field, and again, the field is characteristic 0, so think of the R or Q. Well, it's a vector space that can be written as a direct sum or decomposition like this in a direct sum, where I is an index set. So I would be this index set of the weights. We will keep it nice and clean and simple. So our weights will be always positive integers, just because my application had them that way. But basically in the paper, we actually consider other weights, and this can be done pretty much even for rational weights and all kinds of weights. But let's just, stick it for this talk, stick with positive weights, integer weights. Okay, so now I can write this vector space as the direct sum of these subspaces, okay? And the elements of these subspaces, we call them homogeneous of degree I, where I is the corresponding weight. Now, here is kind of what homogeneous you should think of. It's it's an element in this particular space, right? Subspace, VI. But make no mistake about this. The term homogeneous comes from polynomials. These are the ring of polynomials is a graded ring, and you can split it into this direct sum of polynomials degree, in this case, I. the homogeneous polynomials of degree I, and that's why they're called homogeneous. So anyway, so now an element here, so if you have X, an element which is a vector, which is a tuple of xi's, then multiplying by a lambda, it will actually multiply this way. So the weights here are Q0. I don't know if I said that somewhere. So the weights is, the tuple of weights is this bold Q is Q0 through Qn. I always start counting at 0 because of the projective space, but it doesn't really matter here. Okay, so anyway, any element in V can be written uniquely up to a coordinate change, can be written uniquely as the sum of these homogeneous elements, okay? So this is actually quite nice. And if you want an example of this, like I said, I mean, I will give examples later, but I mean, think always in terms of polynomials. Take polynomials of degree 2 and degree 3 and create the decomposition, I mean, the direct sum of these spaces. So we can define graded linear maps. And what is a graded linear map? Keep in mind that each one of these components is a linear space on its own. And so it is intuitively, it's a map that works on all the components, okay? So, and that intuitive definition actually works all the time here. So it's a K-linear map that respects that grading, okay? That's kind of it. So f of vi is inside that wi, okay? So we can talk about all the set of such maps and so on. We will not need this so much unless we get technical with tensors and duals and all that. Well, I mean, what's the main thing here? I mean, on a vector space, we have what? I mean, at least in Rn, we have a Euclidean distance and that kind of stuff. I mean, we need some kind of a distance in order to approximate and in order to perform any kind of machine learning. So can we actually build that here? And it turns out that there are many ways to do this. So we can talk about this normal operations that you do in linear algebra also for these spaces. We can talk about this matrix. So we define what a graded linear map is. Well, when you go with a linear map from a finite dimensional vector space to another finite dimensional one, we have a matrix associated to that. So there must be some kind of a matrix also here, and so on. So it's actually pretty nice and not so difficult to figure that out. So these matrices here actually are these diagonal matrices, but diagonal in the sense that they have these blocks similar to these Jordan canonical forms and stuff like that. So they have blocks along the diagonal. Anyway, you can define several norms here. So one norm is the so-called Euclidean norm. Okay, so what that does, it brings that weight. So again, keep in mind the vector of weights is Q0 through Qn. So this weight here, Qi, it brings it in front. Okay, so this looks exactly like the Euclidean norm, but it has this little modification there. There is the so-called max norm, max graded norm, and there is also a homogeneous norm, and you can actually define all kinds of things. Okay, so we need some kind of a loss function, right, to build this up. So we have a graded loss function, and these are not the only things you can do it, okay? So a graded loss function is basically, again, something like this. Now I switch to Wi here. That should be Qi. This thing should be Qi to make it to be consistent with the previous ones, okay? So very similar to what you do in the special case, but you have to make these little adjustments with weights. And now you can say, well, why do you do that? Well, it won't be well defined. It will not work if I don't put these little things here, okay, in terms of the norms and in terms of the loss and so on. So, okay, so we'll just have to speed up just a little bit. So now I'm able to define this. I mean, define a neuron. We'll call them graded neurons, okay? So I have now very similar. I have a neuron now this way, just as before, okay? And only in this space, right? And now I have a graded network layer, which is a combination of several layers, okay? Almost everything works the same in definitions, other than you have to keep in mind that each one of these things are defined appropriately to these graded things. So no surprises, the composition of graded networks layers is still a graded network layer, so this model, this network will actually work. So here is my goal, my long-term project, okay? And I'm telling you that right now because this is maybe the good place to state that. Look, now we have a neural network. Can we make this work? Can I define all the machinery that we know with transformers and LLMs and everything in this way? And I believe, well, yes, we can. But I believe it should have been done that way from the beginning. And we lose nothing if we do it actually that way. We only gain. Because what happens? If you take all the weights to be all ones, we get what we have. So this can only improve. I mean, so in a way, I mean, what we have is the simplest case of this machinery with weights. You're taking all the weights to be one. All right, so everything will work with modifications, okay? So we define a graded activation function, and we define the graded ReLU and these exponential activations. So these exponential activations are actually the only thing that it's kind of a little bit new here, okay? So you have these activations that you put lambda to the QIs, or QI is that corresponding weight, okay? For any constant lambda, you put it the exponent of that. So this is kind of something that is not just like that in the classical case, okay? So what is happening? We want to build exactly the same thing. We want to actually have a network, a graded neural network now, and we want to see if how efficient is this, and can I have a tentative, I mean, an approximation theorem here? Does this work in general, as in the classical case? So here is the graded loss. Again, you have to adjust for the weights. Okay, we define a forward propagation and a backward propagation, very similar to what is done in the classical case. So keep in mind, okay, so this matrix of weights here, these are the weights of the learning of the network model. They are not necessarily the grades. So I'm really distinguishing between the weights and the grades, okay? All right, so we have the backward propagation. And it was not clear to me in the beginning when we started in this. I mean, what about things like, are these things differentiable? I mean, do these things like gradient methods and stuff, I mean, would work here? It's really not that popular topic. I mean, honestly, I didn't know, so I had to look it up and I had to see if it would work and so on. But it seems like everything, I mean, I have proved that everything works fine. We will just okay, so what do you do? Here is for the gradient update, okay, you have these block diagonal matrices, and they can be computed in the intersection of the indices, okay? So this is the big O, this would be this kind of complexity. It's a little bit better here, okay? So when you have the data set of size n, and you're given all these layers, we actually have the complexity of a gradient-based optimization. I'll try to see if I can, yeah. So here is kind of a pseudo algorithm, how you would do it for these graded neural networks. Okay, so you have some parameters and you have some initialize some weights and some bias. You have some learning rates, okay, and a given number of epochs. And you'll just go through this very similar to what you will do in the classical case. But of course, you have to apply the graded neurons and the graded loss and so on. So with these adjusted definitions, nothing will change. Then everything else is the same. All right. So okay, I am trying now to make a decision what to cut out of this. So let's just say this is almost repeating the previous one, what we said, but putting it in a more general thing. Okay, so now generalizing these neural networks, a little bit more formally. So this is the reduction to the neural networks. Okay, so basically, this is now a graded vector space. Okay, and now I have this graded neural network. Okay, and it says that this actually is equivalent to the classical feedward neural networks for these exponential activations. It is convex, so for this graded loss, this is convex on the data, which actually assures the convergence. And there is this representation of this. So these are all theorems that are true in the classical case, okay? But maybe not worth it to go through all the details of that. I do have some examples in the paper, so if you want to look at them, I mean, they're not that difficult to follow. Okay, so I will skip some of this. I mean, this is technical, but basically, so what it says is that, yes, it will converge, okay? So this will actually converge, and it will give even a running time or how efficient this is. So look at this little example here, okay? For a simple layer, so I'm taking this very simple vector space with grades 2 and 3, okay? So the loss goes from 10.5 to 0.02 in 100, so the capital N is 100 iterations with this rate, okay? So you do have very good, results for certain cases, So this is the universal approximation theorem comparable to the classical case. So this guarantees that these things will converge, everything will work fine. Again, that doesn't mean that it makes sense. At least at this point, we don't know if it makes sense. It does converge, but is it better than the classical ones? Okay, so let me try to skip a little bit some of this because I want to mention a little bit about the transformers. So here you have this graded Sobolev spaces and an approximation rate in this Sobolev spaces. So then we have this Besov space, okay? Also an approximation on those. So I will share the slides, of course, and this is basically the definition of the Besov space. So you're giving these things for different norms, basically. Okay, so let's just say we have this machinery at least, well, to some point. I mean, we have this neural networks now defined over graded vector spaces. How far can we get this? I mean, can we actually continue with this for transformers and LLMs? And I mean, surprisingly, it works wonderful. So here is what a transformer is in general. So you have a vocabulary of tokens, right? You have basically some RD, so the embedding space, and we have a map. So let's just say T for the transformer. So this is from the space of in features to the space of out features. And theta is this set of parameters that you have taken when you set up a transformer, okay? So I'll make that a little bit more precise. So this is the set of in features, the set of out features, okay? And so this is, theta is this, what we call it, the learnable parameters, okay? So mapping any input here to an output, okay? So this theta includes what? Well, it has something called the attention. I mean, that's what it made the transformer kind of a big thing, okay? You define some attention to it, and you pick kind of what the network needs to keep. Okay, so you have these embedding matrices, you have the weights for the feed forward and normalization and that kind of stuff. So, well, it turned out that for these graded vector spaces, we can actually define two types of transformers. Maybe more, but at least I was able to define two types of transformers. So one would be what I called linearly graded transformer. So this corresponds to a linear graded map. Remember, we defined what a graded linear map or linear graded map was. So a linear map between graded spaces. And now based on that, we can actually define a linear graded transformer. So remember this script tau here, T, was the traditional transformer, right? So what you do, it's not that difficult. So here you have these spaces, RD to RD to the n, right? And you have this graded map. So it takes this thing to this thing. M is the matrix corresponding to this graded map. So this is the matrix that is all diagonal with these blocks, okay? So you have this map, basically. And now, okay, you have the transformer. Okay, here is the standard transformer. And from this, you can actually create now the so-called linearly graded transformer. So what you do is, well, you take the input features here and you send it to the transformer. Transformer is a map, right? So you send it to the transformer of composing it with this T of W, of this linearly graded map. So I wish I had done some kind of a diagram here. In the paper, you have some kind of a diagram that will show you the composition. But it's really not difficult here, okay? Just the composition of this linear graded map and the actual transformer that you have defined the classical way. And so that's why it's called linear graded transform. All right, I will skip some of the details here, but everything is done in detail, so you can go through that, all the norms, and we have an approximator for this kind of transformer and a universal approximation theorem for this kind of a transformer. Okay, so everything works fine. We have this attention, we call it now linearly graded attention. So for every head I, okay, so in a given layer, you have this thing. Notice here, if you actually compare this a little bit with the classical transformer, so you have some adjustments here. So you see the matrix there is the graded matrix and so on. So the adjustments are made that not only they will work, but if you actually decide to pick the grades to be 1, 1, 1, this will fall back to the classical transform. All right, so I'll go through this now and go to the other transformer, which is the exponentially graded transformer. This is slightly a little bit different. Okay, this is slightly a little bit different. So you still have this linear graded map, all right? And now, but this is actually scaled. So you see there is a lambda here. So that lambda here actually goes inside every coordinate and multiplies it with that corresponding weight for each coordinate. So that matrix here is not just MW anymore, but is this MW lambda. So these blocks now all have the corresponding lambda to the QI in each block, okay? So the exponential graded transformer now, well, is similarly the composition of this classical transformer with this map here, okay, with this map here. And again, there is some discussion now, which one is better, but everything here, it will work. So all the this is softmax. Okay, so all the properties are figured out, and basically an approximation theorem should be here somewhere, right? So it's it's already done. So yeah, so it'll work. Now, yeah, I mean, which one is better? And does that depend on the data to decide which one to pick? I wanted to get to your attention before I spend the last few minutes on something else. I wanted to get your attention to something like this. So in general, for example, this exponential transformer, so the key here is we actually normalize this. When we define this, we normalize. It is very similar to what I was doing with the weighted projective spaces, and very similar to what you would do in a projective space. So if you have in a projective space, you have a vector, and you have 2, 4, 6, and 10, you'll pull out a 2 because that's not normal, right? You want to have this to be well defined on a projective space. So something similar is done in the weighted projective space. So you have to divide by that weighted GCD. And so something similar is done here as well. And that is really nice because this in general now, it will match the complexity of the standard transformer, but in some cases will actually be much better, okay? So for example, in our case, when there is graded naturally to your data, this will perform much, much better. So notice here, I mean, the Qmax, you take the maximum of the weights and you define the complexity based on those. So for certain weights that are suited for this, this will perform better. Everything is done now the same way. So we have a graded loss for this kind of transformer. And here you have an example of how you compute that. And we have basically, you know, the training and all of this is. So I need a little bit more time to actually define this in detail. But so this would be some kind of a pseudo algorithm or steps of how you would actually train the data on this exponentially graded training. I mean, exponentially graded transform. And so, you know, you have the weights, and keep in mind, so these are learnable, so you can actually will change these weights now. And for each attention head, you decide, you set, you know, the weights. So you go through the step, very similar. So this is not very readable. So in the denominator here is this capital T here for some reason. Anyway, so it's very similar to what you do. This is this normalization that I was talking about. So you have to actually divide by the norm of these things. All right. Well, has this been implemented? I mean, all of this is good. It tells us mathematically that, well, this works, at least theoretically, but that's not enough, right? I mean, do we have any empirical data on this? And the answer is, well, not as much as we want. So what I did with the genus 2 curves, I extended that and stuff, and that works wonderful. I mean, and I did another project very similar to rational functions, so this moduli space of rational functions. And that's very similar kind of a problem, and it is graded over a graded space, and it works very well. But I don't know how natural this data is, so I would like to actually implement this in a very large kind of a general setting and use it for all kinds of applications and see what it does. But here is some kind of applications that I think probably this would perform much, much better than the classical LLMs. So things that have some grading kind of natural, say algebraic degree or that kind of thing. So it could actually be kind of combined to what we call it hierarchy learning, okay? So you kind of, or including some kind of symbolic thing. So, you know, what I know very well is, yeah, in algebraic geometry, this would be very good. It seems like people have suggested that probably in physics, I'm not too much of an expert to understand how one can use this, but it seems like in physics, people say it could be actually very well. Um, I have pushed a little bit in NLPs, in natural language processing, and I have big hopes on this, especially I'm actually working on a project on that right now, especially to actually do this the training of these LLMs on low source languages. There is this problem in NLPs that not all languages have the same kind of tokens and same kind of data as English, and some languages have much smaller corpora. And can you actually do the training or get good results without having the benefit of all these huge databases? And this is very interesting. Hopefully, something good will come out of that. But I think, well, at least in this paper, we are trying to argue that graded transformers and graded LLMs would actually work much better for these low source languages. And there is some hope that this can be used in these biological systems or networks, neural networks. I haven't pushed this very much. I'm sorry, I wanted to say it here. There is something actually, very big hope. I didn't put it here for automotive industry. And so there are some people actually trying to work on that, but we still don't know. So finally, I think I'll give everybody a chance to ask questions. So this is the paper that was the initial one on artificial neural networks. And then another thing just appeared in this graded neural networks. I have posted a few months ago a preprint on these graded transformers. Haven't sent it anywhere yet, just because I wanted to see if I get some input on this. So if you have projects or problems or you want to try this on, please, I would love that. Thank you.
Tony, thank you very much. Thank you indeed for your talk. And I just want to say up front that I received several emails while you were talking from people who wanted to attend, but due to Christmas period, so they were
That's fine.
traveling. So, but nevertheless, so let me open the time for questions, and maybe I have one maybe rather superficial question for starters, and then we go uh, uh, around the table, so to say.
Mhm.
So, did you apply your graded networks on some standard benchmarks? I mean, so I mean, can you give some sensitive performance advantages?
Well, I mean,
Say
so
graded transformers versus transformers with Q equals ones, so to say.
yeah, so not to the extent that I want, because like I said, I have only applied this and I try to implement this only for the data that I have, which I think it's a biased data because I have built it a priori, this is graded data. And so I think, to be fair, I mean, one would like to actually implement this and try it in random data, and that would be a nice comparison. Theoretically, though, I mean, theoretically, this cannot be worse
Mm,
than the standard transformers because, you know, if the grades are all ones, this will be performing, this falls down to the standard
mm,
transformer, reduces to the standard transformer. But there are some concerns, at least in my mind. For example, this exponential transformer, that this could blow up rather quickly, even though I try to take care of that with this normalizing and stuff. So that's why I think, to be fair, I mean, I would like to implement this. I have a grant pending on this, trying to implement this the right way from the beginning with the grades and everything,
mm,
and see how it performs on unbiased data. I mean, just random data.
absolutely.
That I have not done, and that I think have been probably done already,
Yeah.
but it's not.
Fair enough. So I will return with a couple of my own questions later on. But so we have Dennis and then Josh. Yes, Dennis.
Yeah, please.
Yeah, thanks for the talk, Tony. Yeah, sorry, where's my camera? Yeah, I was curious. You've been showing at some point that you have both the sort of the standard sigma neurons, but then also you have multiplication. And so I was to implement your the graded network. So I was curious if you were looking into this sigma pi networks and if it in some way it's related to the work you've done, either from motivation or maybe from an implementation point of view, it could be related to the sigma pi networks.
I have not. What is this?
Yeah, it's basically networks where people were thinking that, well, maybe addition is not enough. So you also
Uh-huh.
need to have neurons that are implementing multiplication. And just by the fact that we have sigma to denote addition, and then we have pi to denote
I see.
multiplication. So they're called sigma pi networks for that reason.
I see. Oh, that would
So
be very
it might be related in some way, maybe at least
yes.
from the way how you implement such sort of networks. How do you build the actual networks if you would try to do so?
That would be very interesting, actually. I didn't know about this. So the story is, I mean, when I actually was looking at these weighted projective spaces, I mean, I had to come up with something that I defined, I called it like the height of these things. That was actually defined multiplicatively. And then there was actually an addition version of that, similar to when you go to the logs and stuff. So there is a multiplicative version of this definitely. And so I would like to see if it has any relation to these things. I mean, I definitely would be very interested to look at that. There was somebody else, maybe.
Yeah, Josh.
Yeah, Josh.
Hi, thank
Hi.
you. Thank you for taking my question. I was just curious on, so it was on one of your earlier slides. You said that this extends to all Borel measurable sets. It extends continuously to all Borel measurable sets. And I was wondering, and you also mentioned about the vector spaces, frequently looking at vector spaces over R. I was curious, do you have a point of view on what you lose by being restricted? Like what requires you to restrict to Borel measurable sets rather than Lebesgue measurable? And what do you lose, or what might be possible advantages of having vector spaces over other fields than the real numbers?
Yeah.
And
So
part of why I think about the other fields is for things like binary spatter codes. You're looking like it's more like a vector space over F2.
Mm-hmm. So look, I mean, to be honest, I mean, that's what I could prove. I needed this Borel measurable set to make this work. Okay, that doesn't mean that you cannot extend it. I was not too worried about that at the time, so I just wanted the thing to work. So yeah, one can look back at this. I mean, that maybe it's a condition that maybe can be loosened a little bit. And as far as actually going through the other fields, I do a little bit of work with coding theory and stuff like that. And so, look, I mean, everything should work. I think there would be some restrictions, for example, in things like if you have the degree of the thing, so what we call it in algebraic geometry, the situation has to be tame. So, for example, if the characteristic of the field divides the degree of the map, that could mess up things. And as long as you stay away from these things, there is absolutely no reason why this should not work over anything, because vector spaces are defined over any field. They're not defined they're nothing to do with R. I mean, so as long as you stay away from these cases that would collapse everything should work. I have not looked at it but I'm very interested on that because, nowadays quantum error correcting codes and that kind of stuff, it's very important. And I do a little bit of work on that. So, yeah.
Thank you.
Yeah.
So let's see if we have more questions in the audience. Graham, please.
Yeah, I'm quite interested in using large language models, the embedding space, to do sort of logical reasoning using the vectors and then mapping back into the text. Is there anything special about graded vector spaces that would allow you to do different types of logical operations?
I'm glad you asked that. I didn't want to say things that I'm not even sure myself how things will turn out. Okay, but so I reviewed a few months ago something about this tool former. So using LLMs to actually use external tools to improve and to you know uh, get better data. And so this was a project by this group in Meta, which I guess is Facebook and stuff, right? And so they've used external things like math calculators and Wikipedia and this and that and that. So I try to actually see how that would work on these graded networks. And I think I have something. So my belief is yes, this would be much better. And I do have something that it's almost ready, but probably it'll take another 2 or 3 weeks to post it on archive. So yes, I mean you can use grades to actually inject a little bit of symbolic computation and to actually improve the data kind of with what you have by picking the right grades. I mean, you can change these grades in this setup as you wish, and by picking the right grades, you can actually do this. So I do have something I posted a few weeks ago in archive. So if you look in archive, my latest one, that would be in this direction, but I think this could really look. That's my hope. I mean, somehow symbolic computation and logic reasoning is somehow, inserted into this. But
Yeah, yeah. I just want I mean, you can certainly do the sort of standard sort of logical reasoning type things, that the sort of things people used to do with a thing called word to vec, where king minus male plus female equals queen.
right.
You can do exactly the same thing with large language models, but you can do much more expressive things. And you can do these logical operations. I'm just wondering if there are any additional types of operations that you could do in a graded vector space that perhaps you couldn't do in a standard vector space.
Um, I have strong reasons to believe yes.
Okay.
And mathematically, I can tell you in a second what the reason is. So the weighted projective space or the weighted graded space is here. And normally throughout history, I mean, when I looked at this, people say, well, why you want to look into that? Because what we do mathematically, you take that and you project it to projective space, and you do things here in the projective space.
Yeah.
Now, but what happens in that, you take these things and you raise them to a very large power to go there. And when you go to the projective space, computations are super difficult.
Yeah.
And so, of course, it makes sense to do them in the weighted projective space. Computationally, this makes more sense.
Yeah.
You just have to figure that out, how it has to be done. But I think computationally, that should definitely have benefits, because why would you raise them to this? You have to raise things to the LCM of all the weights.
Yeah.
And so that blows it up.
Yeah. I think there's something in the chat that would sort of follow on, because in the graded space you can think of bundling things in different subspaces in the graded space, and that might. Well, let's go on to the next question, because I think that it might be relevant.
But before going to the question, maybe I want to ask Tony, I mean, how much do you know about work being done in the area of hyperdimensional computing or vector symbolic architectures? So do you know anything about it, or did you hear anything about it?
Well, not much. I mean, I think they say that the important thing is not being advertised that much, right? So I
Yeah.
don't know whether these big companies are doing, and we are kind of on our own on this. So yeah, I don't know. I mean,
No, but maybe I mean again. So before kind of a pre-taste to what Tyler is asking. So in this community, we work with kind of uniform high dimensional vector spaces.
mhm,
The overall idea is somehow. Um, expose the similarity structure of some phenomena that you represent with these vectors, and then hierarchies, for example, or data structure in general, also are represented by vector operations in this
mhm,
homogeneous vector space. So we have, and everything is done with, as I said, with respect to some similarity measure. So dot product cosine similarity and such. And typically, so we have just few operations like multiplication, kind of multiplication, then the
mhm,
summation, that what Graham referred to as bundling, and the permutation. So, but everything is done in this kind of q equal one sort of case.
mhm, mhm,
And just to be honest, when selecting or thinking about your paper, so the kind of idea on the back of my head was to to make our community aware about a more principled kind of approach to vector operations.
mhm,
So now coming back to Tyler's question, for example, knowing that we kind of do operations in the kind of uniform high dimensional space, whether you can kind of spontaneously think about um, some maybe new emergent properties
mhm.
imposed by graded vector spaces.
Yeah, I mean, I don't know. I mean, I am not very familiar with the setup, but I wouldn't be surprised of it, but I'm not, I couldn't say right away. I mean, if I knew a little bit more about this VSA, right? I mean, maybe. I mean,
Yeah, but actually, frankly, I'm not expecting any
uh-huh.
kind of immediate answer. So, and
Right.
again, so the main idea with your talk was to, well, to make people aware. So I hope
Mhm.
this recording will be watched by many in our community, and be inspired. So because in my mind, so as Taylor writes in the chat, so. I think one can study theoretically. So, I mean, what kind of, I mean, new properties can emerge uh, uh, if
Right.
you use graded vector spaces for our purposes.
I mean, so look, I mean, one way to think about it, and that's why I had to go through the mathematics first to see if it in general it would actually work or if there was any problem that would stop this working. But one way to think about it is that these graded vector spaces are more general. So they're kind of more general than the vector spaces that we're used to. And so being more general, it kind of have a little bit more freedom, I guess, and a little bit more.
But maybe again, so abstracting away from VSA, I mean,
Mhm,
as a buzzword, as a keyword or something. I mean, you mentioned that Euclidean distances kind of
mhm.
works pretty much in the same way. But what can you maybe comment on the like cosine similarity in graded spaces? I mean, how does it behave? I mean.
I haven't thought about it, but that doesn't mean that maybe other people have looked into this. I mean, I got into this totally from the arithmetic point of view. I mean, I was looking at heights and I was looking at something like weighted GCD and that kind of stuff. So I was
Mm.
looking at rational points and varieties and that kind of approach. Um, I was actually surprised that this has actually extended to other areas and could actually apply to the setup. But I don't know. I mean, I think there is some literature on this from totally the ring point of view, ring theory and commutative algebra and that kind of stuff. Other than that, I think these spaces are very little known to the outside of ring theory. So I'm not too much aware of if anybody is using any of this stuff outside the algebra, kind of extended algebra framework.
Mhm.
So I maybe look when I looked at I was when I wrote this paper on graded transformers and I was looking at all this chat GPT and stuff, and I wanted to find out, has anybody actually used anything like this? I mean, all people have used all kinds of networks. So has anybody used something similar? It did mention something about these bio networks and somehow certain I mean that was not the terms they used, but somehow it did mention that similar things with this bio network, somehow the eye grades certain parts of when it looks at a picture differently and that kind of stuff. So in some way, maybe not in this terminology and this kind of point of view, but in some way maybe this have been kind of looked at.
Mhm.
But I couldn't make much of these bio networks with what ChatGPT was saying, so that is still something to be
Yeah,
explored.
absolutely. But so let's check if we have some last minute questions from the audience. Well, I think we are approaching the end of this seminar. So, Tony, thank you very much one more
Thank
time.
you. Thank you for having me. It was a
Yes,
pleasure.
and I hope it will be inspirational for many of us. So, just remains to say Merry Christmas and Happy New Year to all. And
Thank you.
I see you next year for the new season. So I'm just in the process of preparing it. And Tony, once again, thank you very much.
Thank you very
Goodbye.
much,
Goodbye,
everybody.
everybody.
Thank you, everyone. Thank you.
Bye bye.